In the last video, we talked about Catmull-Ram curves, but we kept our attention on open curves, where the ends don't join. In this video, we'll look at how to make closed curves. To remind you of the difference, here's an open curve. It's like a piece of spaghetti or a shoelace, where the ends are free. And here's a closed curve, where we have one continuous loop, like a rubber band. To make a closed curve, we follow the same recipe as for making an open curve with one little twist. So let's look at that recipe again. We begin with begin shape, and then we call curve vertex once for every vertex in the curve, working our way from beginning to end, and then we call end shape. And as we saw last time, if we do just this, we get a curve that begins at the second vertex and continues through all the knots until we reach the next to last vertex. We only have to make a small change to this recipe to get a curve that goes smoothly through all the control points and makes one single closed curve. So let's begin at the beginning again. We'll draw the vertices and we'll number them. And here is the single closed curve that I want to create through all of them. Here's how we make it. We start with begin shape, and then we call curve vertex for vertex 0, just like before. And then vertex 1, vertex 2, vertex 3, vertex 4, vertex 5, just like before. And last time we stopped here. But this is now where we make the little bit of difference. To draw a closed curve, we keep going. Now, there are no more vertices for us to use, so we start recycling them. We go back to vertex 0, and we repeat it. Then we repeat vertex 1. Then we repeat vertex 2. When we have added these 3 vertices to the vertex list, we can then call end shape, and that creates the closed curve. Now you're probably saying, what the heck? We just list the vertices from the beginning to the end and then repeat the first 3 and that makes a closed curve? And the answer is yes, that's all it takes. Right now, I'm not going to get into the reason why this works. We're going to learn a little bit more about these kinds of curves in future videos, and you'll see why this works. But for now, just remember this is the rule, and it will always work. List all of your vertices, in this case from 0 through 5, and then repeat the first 3. Repeat 0, 1, and 2 again at the end, and you will get a smooth closed curve that goes through all the points. Let me show you these in action. Here's a Catmull-Ram curve made up out of 6 points. I'll make the control points very small so we can see the curve itself. It's nice and smooth. And if I grab these points, I can just pull them around and the whole curve comes along to make a nice, smooth, rubber-banded kind of a shape. So it really doesn't care what I do. I can overlap these things in any way I want, and the curve stays nice and smooth and keeps adjusting. If I turn on fill, you'll notice that processing is smart enough to know which regions are inside and which regions are outside, and it fills accordingly. It's actually doing the same sort of filling that you would get if you drew this with straight lines using vertex rather than curve vertex. So this is actually a lot of fun to play with, and I encourage you to write a program like this because it's a real kick to move these curves around and see how they stay so smooth no matter what you do with them. Let's take a look at how you would actually program up a general purpose routine for drawing these kinds of closed curves. To write our general purpose curve routine, let's start with 2 floating point arrays, and I'll just name them X and Y. Again, ridiculously short names, but I want everything to fit on the screen. In this example, X and Y will each have 6 values. The first value in X and the first value in Y will be the XY coordinates of the first vertex. Then the second value in X and the second value in Y will be the X and Y values of the second vertex, and so on. So to draw our curve, we begin with begin shape and we end with end shape, and in the middle, we just call curve vertex for all of the vertices. So the first vertex is X sub 0, Y sub 0, and then as we saw, it's going to be X sub 1, Y sub 1, and so forth, all the way from 0 to 5, and then to close the curve, we'll repeat 0, 1, and 2 at the end. Now this works perfectly fine if you have exactly 6 vertices. But suppose you had 150 vertices. You don't want to sit there and type curve vertex 150 times. Of course, what we want to do is to replace as much of this as we can with a loop. So let's go ahead and do that. I'll open up some space, and first I'm going to get rid of these 6 lines. I'm just going to write a loop that counts up from 0 to 5 and calls curve vertex for each entry. So let's go ahead and do that. I'll create a little variable called I. It's an integer, starts at 0, and it runs through the length of the X array, which is 6. So the values I takes on are 0 through 5. I also could have used the length of the Y array. They're both the same length. I chose to use X. So what do we do inside the loop? We call curve vertex X sub I, Y sub I, and we have now taken care of everything in the shaded box. So let's get rid of those things and tighten things up. And now we have a much nicer little program. And this will handle curves of any length. Now you could stop here and it would be absolutely fine and probably nobody would bat an eye. But in fact, very few people would actually write the code this way. The thing that bothers me about this little piece of code is that I still have curve vertex being called out manually 3 times. I'd like to get rid of that. I'd like that somehow to get built into the loop. Well, let's take a look at the loop and see how to do that. Right now, the value of I goes from 0 to 5. With that in our pocket, here comes the trick. Let's write down the value of I mod 6, where 6 is the length of the X or Y array. Remember that I mod 6 says, as long as I is 6 or greater, take 6 away from it. So in this case, when I is running from 0 to 5, I mod 6 is just 0 through 5. But remember what we want to do from our drawing. We want to go around from 0 to 5, and then we want to continue for 3 more steps to get 0, 1, and 2. So I'll tell you what, let's just push the loop ahead for 3 more steps. I now goes from 0 to 8. Now we certainly can't ask for X sub 6 or 7 or 8 because those don't exist. X is only 6 elements long. But 6, 7, and 8 mod 6 are 0, 1, and 2. So look at the bottom row. It goes from 0 to 5 and then starts again at 0. This is exactly what we want from our vertices. In fact, what I'm listing for I mod 6 is exactly the sequence of vertex indices that were in the first version of the code. So let's change the code. I'm going to open it up so that the loop runs for 3 more steps, and then in curve vertex, instead of using I'll use I modulo the length of the array. So first let's go up to the for loop, and in the middle clause where I say I is less than x dot length, I'll open that up and say as long as I is less than x dot length plus 3. Now, if I ran the code just the way it is now, it would crash because I would eventually become 6 and I would ask for x sub 6, and that doesn't exist. So let's open up the indices for x and y and put in mod x.length in there. Well, this is great. We have now captured everything in the shaded box in the loop itself. So I'm going to get rid of the code that's in the shaded box and tidy everything up. Now this is even better than what we had before. It's shorter, it's cleaner, but it still has one little thing that I would like to change. Notice that in the call to curve vertex, I am repeating the calculation I mod x.length twice because I want to use the same number to index the x array and the y array. Anytime I see in my code that I'm doing the same thing twice, I try to take out the repetition and do it just once. Suppose I come back to this code in an hour or a month or a year, and I decide that something needs to change, and I go into this I%x.length, and maybe I add 1 or subtract 1. It doesn't matter, somehow I change it. So maybe I change the first one, the one on the left, but I forget to change the one on the right. Now I run my program, it's not going to work right, there's a bug, and I have to spend time debugging it and figuring it out. All because I forgot to change both instances of the very same calculation. So to protect myself, I'm going to compute it just once. So I'll open up the code a little bit, and I'll create a new variable. I don't know, I'll call it not. It's a new integer, and it's just the value of I mod x.length. Now I can take out the 2 shaded boxes and just replace them with this variable in both places. Tighten everything up, and this is our final code. This code will draw a closed curve no matter how long the arrays are, but of course the x and y arrays always have to be of the same length. This is a really nice example of how to take a piece of special purpose code and make it more general purpose. We started with these two arrays, x and y, that held the floating point values of our vertices, and we began with this code. It called begin shape, and then I called curve vertex manually every time from 0 to 5, and then 0, 1, and 2 again at the end to make the closed shape. Step by step, we turned that into the code in the green box. It's easier to read and understand, it's easier to maintain and easier to fix if there's a bug, and more importantly, it's more general purpose. This will draw a curve of any number of knots, and it will always be closed. Here's a Catmull-Rom curve made up out of a lot of points. I'll make them small so we can see the curve itself, and look at how gorgeous this is. It's just smooth and beautiful. I'll bring the points back so we can move them around, and of course I can move around any of these control points, and the curve will always stay nice and smooth and well organized, and it will go through all of the points in order. Catmull-Rom curves are just really wonderful for this kind of thing. They're easy to make, we have our little loop that draws them, and they're easy to manipulate. In the next few videos, we'll take a closer look at how these curves are created, and we'll see some cool tricks that you can perform with them.